Welcome to National Parks Traveler, where we explore the national parks and the issues that involve them.
In the remote wilderness of the Brooks Mountain Range in Alaska, where untamed rivers wind through vast expanses of tundra and towering mountains, a peculiar and alarming phenomenon is taking place. Since 2017, at least 75 pristine waterways, which once shimmered with crystalline clarity, have taken on a haunting hue of orange and now contain very concerning toxic minerals and metals. This is Kurt Repenchek, your host at the National Parks Traveler. As speculation gives way to investigation, a team of researchers has been looking at the region's rapidly thawing permafrost, a phenomenon they suspect may hold the key to unraveling this disturbing transformation. This week, the Traveler's Lynn Riddick talks with key scientists with the National Park Service and the University of California, Davis on their new study that investigates these altered headwater tributaries, including ones in 5 national parks and a number of other protected areas. Among their findings are impacts to aquatic life, ecosystems, drinking water, and the locals who rely on fishing for subsistence. We'll be back in a minute with Lynn's interview.
Smokey's Life. Full of stunning photography and thought-provoking reads, Smokey's Life Journal is a biannual magazine produced by Smokey's Life, formerly the Great Smoky Mountains Association. Members receive it free of charge each spring and fall, and it is available for purchase in retail stores throughout Great Smoky Mountains National Park and online at smokieslife.org. The Blue Ridge Parkway Foundation is the primary nonprofit fundraising partner for the Blue Ridge Parkway. It is made up of people who have a deep love for this majestic road and want to ensure that its natural beauty and the experiences it offers endure for generations to come. Show your appreciation at brpfoundation.org. National Parks Traveler has launched the National Parks RVing Guide, the definitive guide for RVers seeking information on campgrounds in the National Park system. The guide is now available free through the Apple App Store and the Google Play Store. If you're a traveler who wants to explore the National Park system, you'll want this app. The guide is packed with details for campgrounds in more than 70 national parks across the country, searchable by park, state, or region. You'll also find feeds of the traveler's content, including our latest stories and podcasts. Download the National Parks RVing Guide and start planning your next trip today.
At least 75 rivers and streams in Alaska's Brooks Mountain Range are flowing orange, a color in some areas that looks like milky Gatorade or melted orange creamsicles, and is so vivid it can be seen on satellite images from space. With me today are Dr. John O'Donnell, an ecologist with the Arctic Network of the National Park Service, and Dr. Brett Poulin of the Department of Toxicology at the University of California, Davis. They released a study last month looking into this occurrence and found that signs are strongly pointing to melting permafrost as the culprit. Hi, John and Brett. Welcome to The Traveler.
Hi, Lynn. Thanks for having us on.
Absolutely. For those of you listening, I encourage you to check out the written companion piece on our website, nationalparkstraveler.org. You'll see some photos and a map showing the areas where these orange waters are. There's also a good video on the Traveler's website produced by UC Davis. So let's begin with our guests. I want to get into details about what's happening there, but John, would you please start with describing the Brooks Mountain Range, the whole area, how much of the national parks and protected areas are within this expanse?
Yeah, so the Brooks Range is a mountain range that runs east to west in northern Alaska. It covers a huge land area, and the range of our study is nearly 1,000 kilometers from east to west. And there's 5 national parks within our study region in the Brooks Range, and they include Bering Land Bridge National Preserve, Cape Krusenstern National Monument, Kobuk Valley National Park, Noatak National Preserve, and Gates of the Arctic National Park. And there's also other protected lands around this region, most of them run by U.S. Fish and Wildlife Service, So like Canudi Wildlife Refuge, Selawik Wildlife Refuge, and Arctic National Wildlife Refuge. So it's a huge area, very remote. In the national parks where we've been working, there are no roads that go through them. So all access to these sites are through small bush planes or helicopters.
That sounds very difficult to access.
Yeah, I think a lot of these parks are some of the least visited in the national park system. And so, yeah, very difficult to access. And our projects have a lot of logistics in terms of aviation and safety.
Any idea what percentage of the parks and preserves that are sort of affected directly from the orange rivers that are touching parts of the land?
Yeah, so there are many, many rivers and streams in the Brooks Range, and I think what we've documented around 75 is a small fraction of that. I don't have an exact number. Um, the interesting part of this work is that the timing of when these rivers have turned orange, and we can get into more of that later. But yeah, where we have observed orange streams so far have mainly been in Noatak, Kobuk Valley, and Gates of the Arctic. Those are the three main parks. But a lot of major river systems have been impacted, some of which are designated and protected national wild and scenic rivers, like the Alatna and the Salmon River in Kobuk Valley.
So let's get going with the study. So I understand that back in 2018 was when a stream in this area was first observed to be flowing orange. Tell me about how that came about and what the initial response was.
Yeah, so we had been working at a stream, a site for a separate project. This was a long-running project focused on permafrost thaw, and it was also part of the Park Service's long-term monitoring program. And when we were there in 2017, this was a perfectly pristine, clear water stream. And we collected water samples and fish and bugs and other things while we were there. When we went back in 2018, the stream had turned orange. So we were coming in for a landing on a helicopter, and we could see that it had changed color. And so we were, surprised by that, but just we're primarily interested in documenting this change. And, I thought it was potentially just a one-off case study or an anomaly. So we did all our normal sampling that we normally do, and the data were kind of surprising. We saw that the biodiversity of the stream had declined. So these little stream macroinvertebrates that hang out in the bed of the stream, their diversity had declined and their abundance had declined. And while there was a healthy fish population in the stream prior to the color change, after the color change, all the fish had disappeared. We weren't able to collect any, and so that indicated to us that this color change represented a degradation of habitat for aquatic life.
What was your gut feeling at first about maybe what the cause was? Did you have any idea what it could have been?
Yeah, I mean, I might defer to Brett here a little bit, but I guess I would say that we thought that there are other streams in the region that have been orange in the past, and maybe this was just one of those streams. But the fact that we had just gone through a period of warming in the region made me think that it might have something to do with climate. Yeah, so but at that point I didn't think too much about it because it was just one stream out of thousands.
Brett, any thoughts?
Yeah, so John took photos from 2018 and also additional locations where he had seen orange streams, and he asked me what I thought. And I was really surprised to see these photos because my training is on water chemistry and the quality of water. And part of that training, we learn about mining systems. And the photos that John were showing me looked a lot like what we see downstream of an active or abandoned mine. And I used to teach a class on water quality in the Colorado Rockies, where we take students out to these abandoned mines and we'd collect water that's coming out of the mine. And it looked very similar to these pristine rivers in Alaska that he was showing me. And so immediately I had a hunch of what likely was happening, because we know a lot about that chemistry, because we've degraded lots of rivers and streams in the continental US. And so when he collected samples and we looked at our measurements in my lab, we measure a range of different constituents in the water. Some of them are truly dissolved, and some of them are the particles that you would see that make it cloudy. And they tell us about what processes led to the degradation of water quality. They're essentially like a fingerprint of what happened. What we believe is happening is, as the permafrost is thawing, water is getting deeper into the soil and it's interacting with the sulfide minerals that contain these metals. And the water that's infiltrating has oxygen, dissolved oxygen in it. And that oxygen is reacting with the minerals, and it weathers the mineral, which creates sulfuric acid and dissolves all these other metals that are present. And the pH can be very acidic, pH 2.5. And as it makes its way into a river, it then gets diluted and the pH increases. And the first mineral that precipitates is going to be an iron oxide. And that's why the rivers look like they're rusting. The metals that we're seeing include copper, cadmium, and zinc at very high levels. They're so high that we have to specially dilute the samples before they go on our instrument, because they're far higher than you would typically see in a water system. I think one of the assets of this study is that John has established a monitoring network, and he has what we would call our baseline data on what these streams and rivers, their water quality was like prior to these changes. And so I think, John, that was the start, what I would consider really the start of the study.
Yeah, I would agree.
From there, you kind of, maybe, John, you could discuss some of the, I feel like from that point, it was really like crowdsourcing information about where these other occurrences are.
Yeah, because I was kind of curious about what your initial monitoring was looking at prior to observing some of these rivers turning orange. What were you looking at? Where were you monitoring the rivers, and what kind of data were you collecting?
Yeah, so the Park Service, I work for the inventory and monitoring program. And specifically, I work in these 5 Arctic national parks. And each monitoring program throughout the country has its own set of what we call vital signs. And so it's basically like taking the pulse, that's what they say, of park ecosystems. And so I designed a monitoring protocol for the Arctic parks, where we look at water quality, and we're basically looking to detect changes over time. So we look at carbon, we look at nutrients, we look at a range of metals, things like that. And the protocol is designed to go on indefinitely into the future and see what kind of long-term changes we have, but it's also good for detecting new disturbances. So we have a separate project where there were some recent observations of beavers expanding their range into these Arctic parks. And so we've been working on looking at the effects of beavers on water quality. And then we started observing rusting rivers. So there's these sort of emergent disturbances that happen to these ecosystems that we're trying to figure out how they're affecting water quality. Yeah, so that's basically what the monitoring program does.
And so going back to sort of the start of this study, Brett mentioned, it was a bit of crowdsourcing and contributions by a lot of people. Did you feel a little overwhelmed at first? How did you kind of put your arms around this, knowing what you saw and how difficult it might be to start collecting data?
Yeah, so we, after that initial observation of that stream that changed color, we ended up going back out. That was 2018. We went back out in 2019, and we saw a much bigger river, the Agashashok, which is in the lower Noatak River Basin. One of its main branches had changed color too, and it was this very stark color change between clear water upstream, and then it hit like a seep, and then it changed this cloudy orange brownish color for miles downstream. And so at that point, I think we thought that this might be more than just this one little stream out in Kobuk Valley. And we did start to compile observations. We reached out to pilots. We read minutes from subsistence resource council meetings that the park holds. We talked to other scientists who spend a lot of time up there in the region. And after a while, these observations started to really add up. So yes, it was a little bit, I wouldn't say overwhelming, but I would say that we had enough observations to warrant further study. And we ended up writing a grant using these initial observations just to request funds to go pursue this research because these sites are so remote, it requires a fair amount of funding to access the sites in terms of aviation. And so yeah, so that's kind of where it started to take off. Our initial funding was through a collaboration between the U.S. Geological Survey, Park Service, and UC Davis. So Brett, his lab has run the vast majority of samples associated with this project. The U.S. Geological Survey, some of the co-authors there, Mike Carey and Josh Cook, are Mike's a research fish biologist, and so he's interested in the fish and aquatic life component. Josh Cook is a hydrologist and interested in understanding how, when permafrost thaws, how the hydrology changes in these watersheds. And then we also have some folks who are doing the remote sensing piece, USGS, Carson Boffman. And we have some other collaborators through University of Alaska Anchorage and Alaska Pacific University, Patty Sullivan and Roman Dial, who have spent a lot of time out in this region. And we reached out to them to gauge their interest. Roman actually has spent several decades traversing the Brooks Range during summers to conduct his field work. And so he had a lot of observations of rusting rivers that he was able to contribute to our database. And they also collected samples for us. And then we had some other colleagues join from University of California, Riverside, Tim Lyons, and Colorado State. That was David Cooper. And they also have expertise in trace metal cycling and wetlands, microbial ecology, and have spent time out in the field as well, collecting samples. So it really was a group effort. Lots of different folks involved and made contribution to this study.
How did you decide exactly where to pull samples?
Yeah, so once we had established the range of sites across the Brooks Range, part of our decision-making process was to select sites that we're going to be able to access relatively easily, cost-effectively. So a lot of our sites are near this village, the village of Kotzebue, which is the hub in the region, and we can access them within an hour's flight time. And we ended up selecting sites where there are orange or impaired streams and nearby clear water streams, so we could compare the difference between the clear and orange and how the discoloration actually affects the chemistry.
And I wanted to ask you about population in this area.
So the village of Kotzebue is the biggest in the region, and there's a couple thousand people live there. And there's a bunch of smaller villages along some of the major river networks like the Noatak and the Kobuk. And each of those villages has a couple hundred people that live there. Some of the villages, rely on the river for drinking water, and others have groundwater wells, so they're maybe a little bit more buffered from these effects.
And describe the process of remote sensing. What does that involve?
Yeah, so for our study, we used remote sensing, which is basically taking satellite images. The specific ones we used were USGS's Landsat program, and we were able to look at this Landsat imagery over time and look at a ratio of a couple different bands within Landsat to establish what is called a redness index. And so this redness index relates to the iron particles in the stream. It's typically been used in terrestrial settings But Carson, our remote sensing specialist, developed a tool to use this redness index to look at when these streams changed from clear water to orange. And so we have a time series going back several decades that shows for a number of streams, they were just clear, clear, clear. And then the year 2018 hit and they changed from clear to orange. And they've more or less stayed orange since then.
So, yeah, when you look at the photos, it's really not hard to conclude that the water is really compromised. And the study finds that you believe it is the process of melting permafrost and the minerals and metals that are leaching from that into the water. Tell us, for those who don't know, what permafrost is.
So permafrost is ground that has, the textbook definition is permafrost is ground that has been frozen for at least 2 consecutive years. In actuality, most permafrost has been frozen for thousands of years. And it's a mixture of soil and rock and ice. And it's a product of cold climates. So the Arctic, where we work, is in what's called the continuous permafrost zone. So greater than 90% of the land area is underlain by permafrost. And above the permafrost is a thin surface layer of soil that thaws out every summer and then typically refreezes. That's called the active layer. And so there's been a lot of work looking at permafrost, particularly in its role in the global climate. There's a lot of carbon stored in permafrost that when it thaws, it can be released to the atmosphere as greenhouse gases like carbon dioxide and methane. There's been a lot less work on permafrost and its role in weathering processes. So these physical and chemical processes that we're looking at, and a lot less work focused on permafrost thaw and the release of metals. Like I said, most of the work is focused on organic matter and carbon released to the atmosphere. So metal, this is kind of, it's not the first study to look at metals, but it's part of a newish body of literature focused on toxins and contaminants in permafrost zone.
And what are the worst of these metal and mineral offenders as far as negative environmental impacts? Brett.
So it's going to be the ones that we see highest are copper, zinc, and lead in these waters. Now it's not all the same across the different 75 rivers that we've identified, but these metals can be acutely toxic to aquatic organisms like fish. We know that because in the continental US, we have lots of rivers and streams that are affected by similar metal inputs from mines, and they can lead to fish kills. And actually be, when I say acutely toxic, they immediately kill the fish or in a short time after. And so what our study is assessing the concentrations of these metals across the different rivers to assess which are going to be most sensitive for aquatic organisms.
Have dead fish been observed, or have you observed that fish have left areas of these high concentrations of minerals?
So we've observed at the one location where John visited in 2018, all of the fish were gone from that stretch of river. Now, we have not seen fish kills. That's important to note. But the other challenge of our study is that these are remote sites that we might only access once every summer. And so we might not be there at the frequency to actually see that.
So how does the vegetation look like around these rivers and streams that have been affected?
So, well, we, at that one site on the Agashashok River where we were flying over it in 2019 and we saw this big seep, we went back and landed where the seep was originating. It was basically this upwelling groundwater zone on this hillside that was draining into the river. And when we were flying over it, it looked like it had been a wildfire. All the vegetation was blackened. And it, as someone who studied wildfires in the past, I was like, oh, it looks like there was a small little burn here. But we landed and noticed that all the vegetation had just died. And it was from the water that was coming out of the ground. Very acidic, very toxic water had basically killed this big patch of tundra. There were no trees here, just short shrubs and grasses, but totally destroyed. And similar observations have been made in forested areas in gates of the Arctic, where there are these orange seeps coming out of the hillsides. So it can definitely can have a negative effect on the vegetation. In some cases where we've also seen these iron particulates coating the riparian vegetation, the vegetation near the streams, where at higher flows, the iron just gets deposited everywhere. And so, that can also affect vegetation.
So over thousands of years, when the permafrost is created, the chemicals, are they sort of created from the compression of, what's in the atmosphere or what's creating the permafrost? I guess I'm just wondering, how do the chemicals get to be so concentrated?
Yeah, it's a great question. So permafrost can form in a couple different ways, and I won't get too far in the weeds here, but essentially a lot of the chemical constituents that we see in permafrost accumulated there through like burial. So sedimentation, either from like wind-blown silts during glacial periods or deposits from rivers, things like that. And when the ground is frozen, basically all those chemicals are in inert and in an inert state. So they're not reacting. They're just it's like putting something in the freezer and letting it stay there. And when permafrost thaws, you're basically taking all these chemicals out of the freezer and putting them in essentially a refrigerator where they can thaw out, and then they can become chemically and biologically active. And so that's a short answer to your question, but it's a complex question.
And I'll just add that our current understanding is that a lot of the metals are, these minerals, either whether they're consolidated or they've been broken up, they were locked in the permafrost, and those minerals formed over geologic time frames. So actually way further back than the actual permafrost was formed. But when it thaws out, you're essentially allowing all these reactions to then propagate, and they're very fast reactions to happen. So if you just took a mine setting, once you open up that mine shaft, you've created a series of reactions that are going to happen. And we think the same is happening here, where as it's thawed, we've just essentially exposed that mineral to water and oxygen, and that then leads to the acidic conditions and the release of the metals.
And I guess it's your hunch that the spreading of the orange water will just continue over a larger area of land.
We don't know that right now. Yeah.
Yeah, it's a really big uncertainty, and that's an active area of our research, is trying to understand the vulnerability of watersheds across the Brooks Range to this phenomenon. So we know, based on observations and climate models, that permafrost is likely to continue to thaw in the coming decades. But not all watersheds where permafrost is thawing are we going to see resting rivers. There needs to be the presence of these minerals like pyrite in the soils of the watershed. So permafrost could thaw, and if there's no pyrite or no sulfide minerals, we're not likely to see orange streams. But in areas where there is pyrite and permafrost is thawing, that would be locations where we might predict future orange streams to appear.
And is it possible for any of these metals or minerals to settle over time or be diluted with rain and snowfall where they're not so toxic?
Yes, and so there are a series of processes that can mitigate how essentially bad the metals are for aquatic organisms and downstream transport. When we see the orange staining of rivers and that cloudy rust in the river, that's the iron that's precipitated, and some of the toxic metals like copper and zinc could actually adsorb to the surface, so go to the surface of that mineral and then be deposited at the bed of the stream and not be transported downstream. But there's also other there's kind of a natural defense mechanism that the streams have, and that's called their buffering capacity. And it's the ability for them to actually buffer the acidic water that's coming in. And that differs across these different watersheds because it has to do with the carbonate bedrock in the different watersheds, which John has done some work on. And so our current effort to assess that question about vulnerability and the trajectory over the coming years is looking at where the minerals are and where permafrost thaw is happening, and then also assessing which rivers are going to be more or less vulnerable based on their water chemistry. And with those two pieces of information, we can get at risk.
Additional thoughts, John, on that?
Yeah, I think it's so currently I'm in Whitehorse in the Yukon Territory in Canada, and I'm at the International Conference on Permafrost. And this is a meeting that happens once every 4 years. And it's actually been 8 years since their last meeting because they had COVID, forced them to cancel the meeting in 2020. But the theme of the meeting this week is less about, it's focused on adaptation and how to respond to the complete loss of permafrost as we go into the future. Because I think when this meeting started like 60 years ago, people were focused on engineering issues and, very technical, sciencey focuses on permafrost. And now the community, I think, realizes that a lot of the areas where permafrost exists today is, permafrost is going to be permafrost free in the foreseeable future. So it's more broadly, not just resting rivers and metal mobilization. There's a need for the scientific community to sort of understand what the complete loss of permafrost means for ecosystems, for society, for infrastructure, for all sorts of issues. And so, yeah, it's a big challenge. And there's a lot of people here at this meeting who have expertise and are working on answering those sorts of questions.
And so what do you know about the history of melting permafrost in that Brooks Range area from season to season? Is the melting rate speeding up?
We know that in the last decade, there has been a step change, meaning like an abrupt increase in air temperatures through the region. And basically the permafrost tracks those air temperatures. And so between 2014 and 2019, air temperatures took a steep, abrupt increase, and permafrost began to thaw in response to that. And that's been documented in the literature by park scientist Dave Swanson. We know that permafrost can be resilient. So if we had one really, really cold winter, permafrost has the capacity to recover. And then you're starting back at sort of ground zero. But the general trend in the region is warmer air temperatures. The other thing that can contribute to permafrost thaw is deeper snowpack. And so there have been years where we've had really deep snow, and that basically functions as insulation. It protects the permafrost from really cold winter temperatures freezing below ground. And so that combination of snow and air temperature are really what's controlling permafrost. So it's hard to predict year to year what's going to happen, but the long-term trend is one of warming and thawing.
Sure. So to summarize, what were the major conclusions and recommendations of the study?
So I guess I would say that the main take-home points are that we've observed, 75 streams, rivers that have changed color in the last decade, from clear water to orange. And this is all happening in, national parks and protected wilderness areas for the most part. So there aren't any mines. It's just change that's happening to the ecosystems due to regional climate drivers, is what we've hypothesized in permafrost thaw. We know that the water quality in the orange streams is more acidic, has more iron particles and more trace metals than in nearby clear water streams. And a lot of those trace metals are at concentrations where there's concern about their toxicity. We've also observed that this change in color and change in water quality is impacting the life in these streams. So we've observed a loss of fish, a decline in biodiversity of stream invertebrates. And in the paper, we talk about some of the broader implications of these findings, one of which is drinking water supplies to rural communities. And the second is subsistence fisheries. So there's a lot of rural communities, indigenous populations, Alaska Native communities who rely on fish to fill their freezer. And there's concern about the quality of this food supply if the fish are impacted by the metals. There's also concern about the capacity of migratory fish like salmon to be able to move through these resting river reaches and get to their spawning grounds. These are concerns at this point. We don't have a lot of data to back that up, but it's part of our plan to do future research on this work.
Brett, any thoughts?
Yeah, I mean, I think one of the take-home messages is that these change, like when we think of permafrost thaw and changes in water quality, we often can't see the differences, and they often are quite subtle or slow, happening over the decadal time scale. But our study highlights abrupt changes, and some of our data that John collected shows that the change can happen in a matter of days, where a stream goes from pristine to impaired. And it's happening in some of the most pristine waterways in North America. And that should be of concern, because we know that these can be detrimental to aquatic organisms.
Well, so there are still about 1,500 Superfund sites in the US, and many are on that list because of military or drilling or mining operations. Not the case with what's happening up there. But I was curious to know if there were other comparable rivers or streams in the US with very similar concentrations of these same toxic minerals and metals that could be helpful in approaching or addressing the work that you're doing.
Absolutely. So there's a large body of work on the chemistry of metals and their toxicology within rivers, primarily impacted by mining operations. And there's also instances of where these have been remediated, these mining inputs have been remediated, and people have documented improvements and recovery of aquatic systems. And so what we're using as we assess risk to aquatic organisms, we're using that body of literature to actually assess how toxic the metals are or projected to be. One of the challenges we have, though, is that when you go from one stream to the next, there's many differences in their water chemistry, and that can influence how toxic the metals are perceived by the organism. And so that's one thing that we're working on now, is to translate that research and that body of research from these mine impacted rivers to the Brooks Range so that we can assess what the impacts will be.
We have established some relationships across agencies and across other partners to better understand what is happening in the Brooks Range with respect to resting rivers. And so our network has grown, and we have more capacity to collect samples and to make observations and to better understand the mechanisms of what's driving this phenomenon. And I think once we have a better handle on the drivers and what's causing this, and also the consequences for water quality in streams, we'll have a better chance at, one, making predictions or forecasting what's going to happen in the future, and then also providing science-based communication to affected communities and science-based policy or management adaptations to this problem. So we've been getting a lot of emails, communication from people who are planning to visit the parks and what they can do if they can help in some way. So we've provided opportunity for people to contribute their observations of resting rivers. We provided recommendations on if they need drinking water, what to do about it if they don't have any choice. I mean, we definitely want people to be filtering this water if they have to, drink it. And ideally, you're finding clear water streams to drink from. But there's definitely a lot of work to be done going forward, and I think our paper lines out a number of research areas that could be pursued largely to understand both the causes and the consequences of resting rivers in the Arctic.
One of the efforts that was in progress while we worked on this study is we put in a proposal with the National Park Foundation for a Scientists in Parks Fellowship Program. It's a postdoctoral research program, and they selected this as one of the to hire a fellow postdoc scholar to come to UC Davis to work for 3 years. So that's starting later this month. And so we have a dedicated trained scientist that's going to be working on this to help address those questions.
Yeah, and I wanted to ask you, have you spoken to residents of the area?
The National Park Service works with rural communities and Alaska Native tribal representatives to host these meetings called Subsistence Resource Council meetings, and they're held twice a year for the national parks and the Arctic Network. And we've been invited to present at these meetings. We presented a little bit in 2023. So it's an opportunity to have dialogue between Alaska Native community and scientists. And it's really valuable because it's an opportunity to not just be thinking about things from our traditional Western science perspective, but to gain traditional ecological knowledge and insights from people who've lived off the land for many generations and millennia. And so it's been really helpful. Some of those meetings have provided observations that provided justification for us doing this work. I remember there was a meeting in 2021 for Gates of the Arctic National Park, and during their subsistence resource council meeting, somebody from the village noticed that this place where they had gone fishing for many years, and they used to pull a lot of fish out of the river, that section of river had changed to orange mineral, and they were concerned, and that was expressed in the minutes. And we read that and we were like, okay, that matches with some of our observations in Noatak and Kobuk Valley. And so, yeah, I think there's going to be continued effort to keep communicating with people in the region who are affected by this.
And John, you live in Alaska, correct?
Yeah.
And these areas, these parks and protected areas are close to your heart. So how do you tamper this feeling that I'm guessing you have of sort of being alarmed by what's happening up there?
Yeah, I mean, it's a good question. As a scientist, it's my job, especially as somebody working for the National Park Service. It's our job to do sort of place-based science and go out to these parks, even though they're very remote and conditions can be somewhat harsh. But I was definitely surprised when I saw that initial stream observation, and I was more concerned when we started to compile all these observations, because this is a very beautiful part of the country. For a lot of its history, I think these watersheds have pristine waters flowing through them. In the Arctic Network national parks, there are 7 nationally designated national wild and scenic rivers, and those rivers are designated based on their pristine water quality. There's no dams, there's no anything like that. And I think a lot of people view these national parks as a refuge from a lot of the disturbances we see in cities or suburban sprawl or other land use impacts. And so the distressing thing about seeing these wilderness areas impacted like this is that we know it's a challenge to address it, because it's not just one mine, or it's not somebody built a road. It's a large, it's a global effect of having a warming climate. And, the Arctic is warming 4 times faster than the Earth as a whole. And so even though there aren't many people living there, there's still this anthropogenic effect that's impacting these ecosystems.
And I'll just add that this is not a consequence of climate change that we foresaw. There have been observations that warming and thawing in high elevation parts of the Colorado Rockies or the European Alps have accelerated the weathering of minerals, but we never forecast acid rock drainage to be occurring, widespread across the Brooks Range.
Has this kind of thing been observed in other parts of the world?
Yes, so there are several instances of people observing a climate-driven acceleration of mineral weathering. But one of the key distinctions is that all of those locations already had the mineral weathering happening. So it'd be like the river already had some orange staining and it got worse. And what's unique about our observations is that we weren't observing it in the vast majority of these watersheds. There were no instances or observations. And we even went back to some of the initial U.S. Geological Survey reports of the Noatak River and others, because they did water chemistry assessments and they had lots of written documentation and could only find 2 locations in the whole Noatak River that had observations of iron inputs, and they were at well-known springs. And so none of the locations that were observing it.
John, at your conference, is there any discussion about likely places where this might happen in the near future?
So I'm giving a talk this afternoon at the conference, and I'm actually looking forward to connecting with more researchers who are doing similar work. Right now, I don't think there are that many of us, but I know there is one other person who's doing a remote sensing study of resting rivers, and she's presenting here at this meeting. But to date, there haven't been many studies on this topic, and I think our study will hopefully be one of the first, and will spawn follow-up research by the community. But I am particularly interested in getting feedback from the permafrost community on our observations, because we've laid out some hypotheses, and it'd be great to see what the permafrost community has to say about them.
All right. Well, John and Brett, I really appreciate your time. I thank you for being with us, and we'll continue to follow this issue as you will. So thanks again.
Thanks
for having us.
That's our show for this week. We hope you found it interesting. To learn more about the stained rivers, look for Rita Beamish's story about the phenomenon on the National Parks Traveler in the Features queue. Next week, we'll be catching up with contributing editor Kim O'Connell, who has been at Cape Hatteras National Seashore working on several stories tied to the seashore. For The Traveler, this is Kurt Repenchek. See you in the parks.
The composers and musicians at Orange Tree Productions have created a unique collection known as the National Park Series that has grown to include more than 30 CD titles. Composed against the backdrop of a park's sounds of nature, these musical scores will connect you with these beautiful places and take you there, at least in your mind. This collection is the #1 selling National Park audio series in the world and provides the background music for National Parks Travelers podcasts. Visit them at orangetreeproductions.com. Editing and production work for the National Parks Traveler podcast is done by Splitbeard Productions. You can learn more about us at splitbeardproductions.com. National Parks Traveler is a 501c3 nonprofit media organization that provides daily editorial coverage of national parks and protected areas. Traveler's coverage is made possible by reader and listener donations. Visit us at nationalparkstraveler.org.